Let me know when we're ready.
Okay, looks like we're live.
We're live? Okay, let's get started. Welcome, everybody. Welcome to the Ultimate RISC-V. Today, we have a prime lineup of speakers to share with you their experience in development and research with RISC-V. This is a live broadcast, so we're inviting you to drop your questions in the Telegram channel. If you don't know where that is, that's in the YouTube description. So head over there and you'll find the link to join the Telegram. And if you're interested in continuing the conversation from tonight, go ahead and stay in that channel. We'll be continuing to keep it going from there. So without further ado, I'd like to bring up our first speaker, which is Matt Quinn from the Nervos Foundation. Matt, take it away.
Tell me you can see the full screen. Okay, looking good. Okay, great. All right, so today I'll be talking about CKB and RISC-V. So I want to welcome everyone to the event. Good morning, good evening, good afternoon, wherever you're coming from. The topic at hand is RISC-V. First, let's get a proper logo in there. RISC-V is an instruction set. And naturally, the next question is going to be, what is an instruction set? So inside of, well, first we need to journey inside of a computer, then we'll find out. So inside of any laptop, desktop, smartphone, any computer of any kind, you're going to find a processor. And this is the brain of a computer. Everything the computer does, all of its thinking is coordinated by this component. And an instruction set is a type of language that this processor understands. This is the language that ultimately software will use to communicate with the hardware itself. And the language of the processor is different from programming languages that you might think of when you think of a language for a computer. It's the kind of language that you would see in punch card computers in ancient times. It's super abstract, and it's not the kind of thing that people are going to be able to make sense of, but for machines, it's easy. Now, even though people may write code like this, ultimately, it's going to get compiled or translated down into extremely abstract code that can be executed by a computer. There's two dominant languages in the world today. There's x86, which is owned by Intel and AMD, as well as ARM, which is owned by ARM Holdings. x86 chips are found in desktop and laptop computers, while ARM chips are found in lower power devices like mobile phones, and most recently, even Apple's M series of chips. The only way to legally use one of these instruction sets to create a chip is to acquire a license from the company that owns it, whether that's Intel or AMD for an x86 chip or ARM Holdings in the case of those chips. Now you can imagine there'd be a number of reasons that people might want to break this monopoly. Maybe people might just out of principle think that computers shouldn't be the kind of thing that some company should have a stronghold on. Or maybe from an economic perspective, people may not be able to actually make their products when they have to operate at the whims of these companies. So enter RISC-V. RISC-V is an open source, open standard instruction set which allows anyone to make a chip. There's no licenses required. It's licensed under Creative Commons. It was developed at UC Berkeley starting around 2010, and this was the 5th iteration of the RISC architecture built by the university. Their first work began in the 1980s. RISC-V is modular. Its capabilities can be expanded with extension, and it's undergone a rigorous standards process over the course of many years. You can find RISC-V in a number of devices. Many of them are these single-board computers, and RISC-V has found a home across a number of different industries, including AI, machine learning, aerospace, automotive, in data centers, and in consumer devices. The RISC-V ecosystem is second to none. You can see the largest of tech companies have joined this effort for RISC-V, including Google, Samsung, Qualcomm, and more. Google has even announced efforts to run Android on RISC-V. So we may see a day in the future where we have a large number of RISC-V smartphones running in the world. But it doesn't stop there. RISC-V has even become a topic of conversation for governments across the world, most notably for trade tensions between the United States and China. In late 2022, the US ordered that ARM Holdings would no longer be able to license the ARM instruction set to Chinese firms. With RISC-V, companies producing these devices can continue their work. RISC-V has grown significantly in China as a result of these sanctions. And additionally, Russia and India have expressed interest in developing RISC-V chips of their own so they can end reliance on those companies that have to license these things. Today, RISC-V International counts more than 3,000 members and across 70 countries, and over 10 billion RISC-V cores have been manufactured in the world. So we know what RISC-V is now, but what exactly does this have to do with blockchains? So we can start by comparing a physical computer with a network of nodes that make up a blockchain. So these are both hard to change. Physical hardware can't be modified once it's produced, and any breaking changes to a blockchain will require updates to all nodes. But we're talking about high technology here. These are systems that are going to need to adapt to changing requirements in the world. Additionally, we want to prioritize backwards compatibility. We want to ensure that any upgrades we make to our hardware, to our blockchain, don't break anything that's already in place. Lastly, all instances of a piece of hardware or a blockchain need to operate exactly the same, whether that's nodes that need to stay in consensus or a piece of hardware that needs to remain compatible regardless of the peripherals you plug into it or the software you run on top of it. So we can see that there are similarities in the solutions that are needed for RISC-V and for a blockchain. So what exactly does RISC-V give us? Most importantly, it's a shared open source standard, and this maximizes compatibility across implementations. And because RISC-V is an actual computer, it provides maximum flexibility to whoever's using it. And the R in RISC stands for reduced. RISC-V is actually a small, simple instruction set, and this makes it quite easy to implement things. I was speaking with Jan right before we got on the call about how quickly he was able to prototype and develop PolkaVM, and we're looking forward to hearing more about his work shortly. RISC-V is also convenient to estimate the amount of effort, of computational effort it's going to take to execute it. And this makes it easy for protocol designers to make assumptions about things like gas, I guess would be the simple way of saying it. So in blockchain, what has been done with RISC-V? We see, there's Nervos CKB, which I'll talk about in a second here, which is a generalized UTXO-based blockchain like Bitcoin. It's a layer 1 with a RISC-V virtual machine. There's also Cartesi, which runs a Linux VM inside of an Ethereum rollup framework, and this is an L2. RISC-0, also an L2, is a ZK general computation platform. And the newcomer, PolkaVM, which soon we'll hear about. From what I understand, it's a high-performance virtual machine intended to be used for blockchain microservices on Polkadot. So that will also be an L1. Let's take a look back at the history of RISC-V and blockchain. In 2018, the CKB white paper was written, as well as the Cartesi white paper. In 2019, CKB launched. In 2020, Cartesi released an SDK to build, I think it was rollups. And we also saw Ethereum accounts used on CKB, which to my knowledge is the first use of account abstraction in the industry. RISC-0 started in 2021, and 2022, in the deep bear market, it seems like everyone was building. I couldn't find much to talk about. But 2023 has been a big deal for RISC-V, and RISC-0 has released the ZK VM. Cartesi has launched a rollup. PolkaVM has started. You can check out more. It also looks like RISC-V can provide some efficiency gains for ZK VMs, and you could check out that work in this QR code. So now I want to move to talk about how RISC-V fits into the goals of CKB. First, I want to say that the vision for CKB is a verification engine that anyone can run, and this is the foundation of a layered blockchain network. CKB takes a lot of inspiration from what has worked for Bitcoin and prioritizes robustness and longevity over performance. And this means that CKB is primarily concerned with being secure and decentralized, while L2s are used to scale, things like channel networks or rollups. And you can see here over 300 CKB nodes are online right now. how exactly does CKB help, or RISC-V help CKB achieve these goals? So the CKB VM is a RISC-V interpreter. It runs at about 100 to 200 transactions per second, which is adequate performance with CKB and doesn't introduce any of the considerations that come with a JIT approach. In this way, RISC-V can, or CKB can run on any platform, anything from a laptop that you're watching this on right now to a Raspberry Pi or even a smartphone. Efficiency can be improved with extensions. A few have already been implemented, and the vector computing or V extension is considered impossible for the future. You can read the research in the QR code there. I felt like this meme fit the CKB doctrine pretty well. The idea is there's no way that designers of a system are going to be able to comprehend how it might be used in the future. So it shouldn't really be optimized to be used any particular way. Rather, it should be a general machine that can be used by developers as they see fit. And with this, we're operating at the lowest level of abstraction. There are no semantic constraints on developers, and this means there's less hard forks without any sacrifice of flexibility. It also means that the governance hassles and the changes that certain factions want to make kind of get avoided. Preferences about what exactly this development environment should be or how it should operate can be handled at the smart contract layer, and you don't need to go through the process of coalition building and hard forking to change the underlying chain. Now, because RISC-V is a stable and well-supported base, existing off-the-shelf tooling and open source code can be seamlessly used. Things like cryptography or compiler tool chains like GCC or LLVM. And we see in the CKB auth project that this team has been slowly but surely adding support for a number of different chains that interact with CKB. And of course, all of this is efficiently executable on any hardware because of the magic of RISC-V. So I've gone over a lot of basics, a lot of fundamentals, but I want to go through what is actually being done on CKB. So first we see passkey wallets. This is Joy ID. It's a non-custodial, demonic-free, multi-chain passkey wallet. It has advanced account features built on CKB. It launched a few weeks ago, and we're just seeing what it's capable of. Next, chain-agnostic decentralized identity solution called D.ID. So you can see that users can select from a number of different wallets that they can use to control their ID. They may not even know that they're using CKB under the hood. They may even be using a passkey, with a Web 2-like experience. But all this is made possible because of using RISC-V with CKB. We also see compressed NFTs. This is an NFT standard which leverages a sparse Merkle tree to deliver close to zero-cost NFTs. Also see single wallet bridging UX. You can check out this Ethereum bridge, which allows for moving ETH and ERC20s over to CKB without ever leaving the Ethereum wallet. And while this experience could be extended to be working with other chains, bridges are risky, and the transaction signing standards that would be needed for this to be secure are non-existent today. We've put a lot of effort into trying to realize this, but it's unfortunately a little too early for this kind of magic to be ubiquitous. A ZKVM has also been successfully tested on CKB. You can check out the link here for a write-up and to learn more. Quantum resistance has also been tested successfully. CKB can be held outside of the reach of tomorrow's quantum computers. For programming language support, Rust is well supported. There's a development framework here. There's been a good amount of work on Lua. You can read a guide here about programming with Lua on CKB. And JavaScript support is also available, but it's very much a sandbox kind of thing right now. I encourage anyone who's interested to check out the repo here. Last but not least, Taproot, Bitcoin's high hope for programmability, is also supported on CKB. You can check out the linked article to learn more about Taproot becoming enabled on CKB. Okay, this is the fun part. Lessons learned in building CKB for others looking to build virtual machines using RISC-V. First off, most developers today aren't used to managing memory, so writing contracts in C will hinder adoption, which seems easy enough. Additionally, regarding memory, CKB VM caps available memory in the interest of security, but unfortunately, this does not solve all problems, and doing modulo math on address overflows might be better. It does add some additional contract checks, but it could unlock some performance benefits as well. Also, consider a minimal memory management unit. Without it, unexpected problems that are hard to debug could pop up. And one last detail, support for the C extension increases or decreases overall program size, but increases complexity when you're optimizing for performance. However, Rust by default requires C extension support. So seems like you need Rust, but what are you going to do? So this was a glimpse into the rabbit hole of RISC-Vs and blockchains. So the question is, where does one go from here? Honestly, the power is in your hands. RISC-V to me seems to be an absolute game changer for blockchain systems, and I cannot tell you how excited I am to be having this conversation here today. The ability to implement new virtual machines and maybe even machines and hardware that are vastly more performant and flexible from the blockchains that we see today is very exciting. And seeing RISC-V also having a narrative in ZK and possibly bringing these benefits to verifiable computation, also super exciting. And entering this world where we're using open source tools instead of this super bespoke web of chains, chain-specific tooling, it's really cool to see RISC-V kind of taking off. And from my end, I'll continue to advocate for CKB and in-protocol account abstraction and the magic of UTXO-based applications, any cryptographic primitive, any programming language, different VMs, L2s, transaction semantics, new data structures and algorithms, and most recently, trust minimized light clients on CKB, which are a first from what I've seen. And yeah, I am really excited that RISC-V has piqued your interest, and I'm looking forward to learning more from everyone we have gathered here today and journeying toward the future with all of you. There are developers waiting on the Nervos Discord to help anyone building. Please check out these links from the community. And yeah, with that, I guess I'll pass it back to Jordan for our next speaker.
Looks good. Looks clear.
Yeah, let's go.
Okay, thank you. Yeah, a second. Okay, so hi, I'm Jan. I work for Polkadot at Parity, and today I'm here to tell you about PolkaVM, which is our new RISC-V based virtual machine. So first, a little bit of history. Since the very beginning, Polkadot was essentially built on WebAssembly. In particular, one of our unique features is that our state transition function, which we call a runtime, and which essentially contains all of the business logic of the blockchain, is a WebAssembly program that we can just dynamically upgrade in easy, forkless upgrades. And also our native smart contract solution is WebAssembly based. So we're very much heavily invested in WebAssembly, and we care about a lot about its speed. In hindsight, I think picking WebAssembly was absolutely the right choice here because like there weren't really any other good alternatives back then. And in general, we are happy with it, but there are some problems. For example, WebAssembly is actually pretty complex. There's no stable baseline and it's constantly growing. The very first minimal viable product of WebAssembly had 172 instructions, and that's up to over 400 today. So that's quite a bit of growth. And if we count all of the current proposals which are in flight, we get up to 541 instructions. So this is quite complex. For comparison, if we look at the current king of complexity of instruction sets, which is the 64-bit x86 architecture, it has, depending on how you count, 2,000 instructions. So WebAssembly is 1/4 of that. That's a lot. And the compilers are gradually starting to use those new instructions by default, often with no prior warning. Like, for example, most recently, the sign extension instructions were enabled by default in LVM, which did surprise multiple blockchains, including us. It's also not 100% deterministic, and if you have a blockchain, you do very much need 100% determinism. It's an absolute requirement. The exact bit patterns of floating point, not a number, values are unspecified, and the size of program stack is unlimited and might overflow, among other things. So it's not a total deal breaker because you can work around this, but it's really annoying. And WebAssembly is a pure stack machine, and real hardware is not. So this means that when you want to execute a WebAssembly program in an efficient manner, you need to reduce it into a register machine. And register allocation is an NP-complete problem, which basically means it's really hard and it's really expensive. So it's hard to have fast execution and fast JIT compilation times with WebAssembly. So can we do better than that? Ideally, we would like an instruction set which is like a register machine. So it's easy to run on real hardware. It's simple and has a stable baseline and doesn't change underneath us by itself. It's portable. It's well defined and standardized. It's already widely supported by compilers. We do not want to maintain our own toolchain. That's something we absolutely don't want to do. It's guaranteed to be supported into the future. We're looking at timescales of like 10, 20, 30 years. Has enough features to compile arbitrary existing programs, but it doesn't force on us features which we don't want or need. So wait a minute, doesn't that sound just like RISC-V? And yes, exactly. That's what we were thinking when we surveyed this whole landscape of alternatives to WebAssembly. So we decided, hey, let's try a new VM and see how it goes. So the very first prototype for PolkaVM or new RISC-V based VM was written in only 2 days. Granted, those were very long 2 days, but it were 2 days nonetheless. And it was a full JIT recompiler which recompiled the RISC-V code into fully native code. And the funny thing is, this prototype written in 2 days was already faster than some of the production VMs used today on some of the chains. So we were like, this looks really promising. Let's try and go all the way in and see how far we can take this. And here we are today. PolkaVM is still a research project, but it's slowly approaching production ready status, and the current version already achieves state-of-art results on several metrics, and we're not done yet. So execution performance, this is how fast one of our benchmarks runs. And on the very left, we have native. Also, keep in mind, this is logarithmic scale to make the graph readable. This is not linear. So on the very left, we have native. This is essentially the benchmark executed natively just on bare metal on the CPU, right? And we have 3.8 milliseconds, quite fast. And in the second place, we have PolkaVM, 5.7 milliseconds, so almost native performance. And in the third place, we have WASM time, which is essentially the gold standard for WebAssembly VMs. And this is the WebAssembly VM we are currently using. So we are already slightly faster than the WASM time, which is quite amazing, because PolkaVM has been in development for only a few months, and WASM time has many years of effort put into it, and it's very well optimized. So these are great results. In the fourth place, we have WASM single pass, and this VM is notable for the fact that it's essentially, unlike WASM time, it guarantees linear time single pass compilation. So this is, for blockchains, this is very good for security, because you cannot then denial of service attack the chain with a special crafted program. Then we have Solana RBPF. They're using eBPF as their instruction set, and their performance is not that great. And in the last place, we have WASM, which I put it here just for comparison, because this is an interpreter written in pure Rust. So this is essentially as fast as you can go, more or less, with an interpreter without any assembly tricks. So this is great, but this is only execution performance, and we also care about compile time performance. So how long does it take to translate a program from RISC-V into native code? And we're already we're also pretty good here. We are in the first place with 427 microseconds, and the second best is Solana. Might not be that great, but they have really fast compile time, so that's something they got right. And on the very far right, we can see WASM time, which is pretty slow when compiling. So this is how they get their stellar performance. They just have a really powerful optimizing compiler, which takes quite a long time. So PolkaVM features as of today. We essentially execute as fast as WASM time, but we are over 160 times faster to compile. We compile faster than Solana, while being over 12 times faster executing than them. We guarantee linear time compilation, so you cannot denial of service the VM by crafting a specially malicious program to blow up the compilation times. We guarantee 100% determinism out of box, so you don't need any workarounds to make sure the execution is deterministic. We are secure and sandbox by default. This is something that I haven't seen any other VM do. Most other VMs just run their guest programs within the same process and hope they are secure, which usually works, but bugs happened. So we took a different approach. We assume that we have bugs. So we always run guest programs in another process. So if it misbehaves, it cannot do anything malicious to the host. We also run them in another namespace. This is essentially exactly the same technology as Docker uses. So the guest program, even if it breaks out of the sandbox, it cannot access the network, it cannot access the file system, it cannot access any other processes because it's fully namespaced, just like Docker containers are. And our guest programs also run under a strict seccomp sandbox. What this does is basically it blocks the vast majority of syscalls, which are essentially calls into the Linux kernel to request some servers from the operating system. And you have something like, I don't know, 200, maybe 200 of them in total. So we actually need only, I think, 6 of them. So we block all of the rest. And this is quite important because most of the kernel exploits actually happen through some obscure syscalls that are not commonly used. So this reduces the attack surface quite considerably. And we can also run arbitrary C, C++, and Rust programs, which is not true, for example, for Solana's VM, which has quite severe limitations on what you can run there. But that's not something I will elaborate here. Oh, and we also have really fast gas metering. Gas metering is essentially a feature that you need for things like smart contracts, right? And we implement essentially two kinds of gas metering: synchronous gas metering and asynchronous gas metering. And the difference between them is quite simple. With synchronous gas metering, before you execute a piece of code, you essentially consume the gas and check whether you are out of gas or not. If you are out of gas, you abort the execution. If you still have gas in the tank, you continue, right? So asynchronous gas metering removes the check for the gas, and gas is instead checked from another thread running concurrently with the program. So this makes it a lot more efficient. And for the majority of use cases like smart contracts, you don't actually need synchronous gas metering. So you can have this essentially free performance uplift for like with no downside essentially. And the funny thing is, when we are running with gas metering, we are faster than WASM time, which is running without gas metering. And our gas metering in general is faster than theirs. And okay, so our VM can do quite a lot. Can run Crisis? Not yet, but it can run Doom. I have ported Doom to our VM, and it runs fully within the VM, including the graphics and the sound. Everything except I/O, obviously. So input, output, you cannot encapsulate that fully within the VM because the user has to interact it with somehow. But everything else runs inside of the VM, and you can play through the whole game like this. Here's a link. You can git clone the repo and play it yourself if you want. And we also run Doom on our CI. So on every commit, we actually check that Doom still runs and that it works correctly. So we are probably the only VM in existence which runs Doom on its CI. So what's our secret sauce? Like why we have managed to achieve these results in only a few months of work? So our first secret sauce is RV32E. This is an embedded variant of RISC-V with only 16 registers. But in reality, it's only actually 13 because the zero register doesn't really count, and the compiler by itself doesn't emit code which uses the GP and TP registers. It was quite recently ratified in January of this year, and the toolchain support is not there yet, but hopefully soon it will be. And this is perfect for a recompiler into an instruction set like 64-bit x86, which only by itself coincidentally has 16 general purpose registers. And this is because we can essentially map every RISC-V register one-to-one to a native register. So this makes code generation really, really simple, because you don't need to spill any of the registers into memory. And it also allows the compiler to essentially optimize the code for 16 registers. Our secret sauce number 2 is the sandbox. This is not just for security, actually. We have a specially crafted ELF file, which the VM launches, which guarantees that the lower 4 gigabytes of other space of the process are free and can be used by the guest program. And this has the magic property of allowing us to have really cheap single instruction memory accesses. So here we have 2 bits of assembly, one generated by PolkaVM and one generated by WASM time. So as you can see, we can do this in one instruction, and WASM time needs 3 significantly more complex instructions. So this makes it quite a bit faster to access memory. And our secret number 3 is our compilation pipeline. Basically, we do not, the VM doesn't actually load the files that a compiler spits out. What we do is that we use a standard toolchain, so your standard RISC-C, Clang, or GCC, and we compile the program into a standard ELF file. And then what we do is we have our own linker, which takes that ELF file and post-processes it. So this linker does things like it does relocations. So now we don't have to do relocations in the VM, the linker does it. It does macro op fusion. So basically in RISC-V, for example, if you want to load an immediate value into a register, if the immediate is too big, you need 2 instructions. But we are a VM, we don't have such limitations. So what we do is that we merge those 2 instructions into a single one. So that's essentially macro op fusion. And we do this in the linker. So the VM by itself doesn't have to do this. We also do some other minor optimizations like extra inlining, constant propagation, dead code elimination, etc. So the general idea is to move as much complexity as we can into this linker and keep the VM as simple as possible. So the linker runs offline and generates a program blob, which then the VM can load and generate native code. And this works quite well. And so what about the future? We are not done yet. We're planning even more performance improvements. Ideally, we would like to be as fast as native code, as natively compiled programs. We may or may not get there, but we will certainly try. And there are quite a bit of things we haven't tried yet. So even more macro fusions. So we're currently fusing essentially only immediate loads, but there are quite a bit of other macro fusions which we could be doing, which could improve performance. There are also a bunch of other RISC-V extensions which we could implement. Currently, we're just supporting the M extension, which is the multiplication extension, and besides that, we are plain vanilla baseline RISC-V. So there are quite a few interesting extensions, like the bit manipulation extensions, which were ratified some time ago. There are those T-head extensions that are vendor specific, but some of them are very interesting, and we think they might improve performance quite a bit. And we also want to add 64-bit support, because we're currently only 32-bit. We're also planning on adding even more features, like dynamic link of multiple programs at runtime. Time travel debugging is also something we want to have, which, as far as I know, no other VM supports. Basically, what is time travel debugging? When you're debugging a normal program in a debugger, you can only go forward, but with time travel debugging, you can also go backwards. So this is really cool. This is a really cool debugging feature, and thanks to the fact that we are 100% deterministic, this should be quite easy to implement. And we also want to support running on other CPU architectures, because right now we're only supporting 64-bit x86. So the major candidates here are 64-bit ARM, namely the M1 Apple Silicon chips. We want to be able to run on them. And of course, native RISC-V. RISC-V is not there yet with hardware, but maybe in the future, when we will have really high performance RISC-V servers, we want to be ready for that. Also, we also want to do some research on coming up with better cost models for gas. So we want to figure out if we can lower the gas fees by more closely modeling how modern CPUs work, which is something that we think is a worthwhile research direction. Also, we do want to write a proper spec for the VM before hitting version 1.0. So we want to have a comprehensive test suite as part of the spec, which will be independent from the VM, and we want to make it really easy for someone else to just implement a new VM that is 100% compatible with ours. And this will also help with long-term support and stability. So that's all I have for you today. Thank you. You can check out the code at the following link. You can also, if you want to talk about this, you can message me on Element, or you can just email me. And that's all from my side today.
Hello everyone. I'm popcorn from Rooch Network, and it's a brand new layer 2 project for scaling the throughput. We use Move as our smart contract language. Okay. And today the topic we are going to dive into is enhanced ASIC verification in layer 2 and using the power of RISC-V. We will be discussing my thoughts about the role of RISC-V in enhancing ASIC verification in layer 2, and I look forward to sharing the insights and the ideas with you. And okay, let's get started. It's evident that the content I'm sharing today is not complex in terms of logic. As I have screened out the details of I don't share too much details of the implementation. I am for the content to be concise rather than getting lost in the sea of the details. And I think the most important is to configure the problem we are addressing and why RISC-V can help. Okay. In the first topic, I want to show the background of the async issues in blockchain world, and after review that, we will find another new issues have to fix. So that's we need a deterministic language to connect each row in the whole process, and it brings new problems. So we need an answer. The answer may be the RISC-V, but we need to go further. So we check the details of RISC-V in the last topic. So the first topic, I think, why it's an issue and why we need a layer 2 solution. About 18 years ago, the most powerful man in the computer world in that age, the president of IBM, he think maybe we only need 5 computers, and that's funny because in each blockchain world we only have 1 computer. So but the real issue here is that we have to wait for the sync verification results, because the bigger network we have, the result will be more reliable, and the cost is high, the latency is high. So how could we shorten the distance from users to the blockchain world? There is a very straightforward answer, because it's a sync verification, so we could change it to async way. But how? Because it's just a very simple idea, and this figure show how it will look like. We only have one logical node. Maybe it's good or evil. It just return the results and waiting for the network behind it to check the results. That's how the optimistic rollup works, and there are many and there are various ways to do the async verification. But today I only focus on the optimistic rollup. Okay. So in present, maybe we have achieved something, but it's still far away from making it really work. So, what's the next question? The new issues. It's quite simple because if different people from different place they want to talk the same thing to get the same results to make the agreements, they have to speak in same language. In the optimistic rollup, we have 3 rows in 2 layers. In layer 1, as we all know, it's the blockchain, such as Ethereum, and Nervos, and so on. And here is a VM. He speaks his language, and there are 2 rows off chain in the layer 2 layer. In the layer 2, and there's a defender which who submits the result first on the layer 1, but someone disagree with it, so he want to challenge the results. But what language they will use? How can we choose the right one? So many people have to have done much efforts on it. It's obvious we need a deterministic language because we want every step could have a proof in this environment. So it must be a emulator. This emulator could run each part of the whole process in everywhere. So there is a very straightforward answer is that we use, for example, in Ethereum, we use Solidity directly. We could choose the results. So yes, levels of team have done a lot of work on it, but the field. Here I give the result why it's so hard to build it with Solidity, because the space-time limitation. The space-time limitation means each state is related with another event, because the timeline is made of made of events, the causality between events. So for example, I give some code to show how well related with the timeline. So we cannot turn back the error of the time. It's hard to just get one piece of code and replay it. So that's not what we want. So we need to find another solution. Okay, and here is a answer, potential answer. it's still very straightforward because we could run a VM in VM. But in this approach, it's obvious the cost is so high. I mean the gas cost, and the cost of implementation is high too, because there are still some side effect operation. It's hard to implement in this way. For example, the memory, the storage operation. So so in community, we almost give up this solution. So what's the answer? What can we what can we do to handle this issue? Not just me, and many teams, many projects have given their answer is RISC-V. Why? But why? Okay. RISC-V. First, it's I put two manual on this page. You could see in the x86 CPU, we have to facing so many instructions. We have to implement so many. We have to handle so many details, and in RISC-V is so simple. It has a really simple instruction set. It will help us to implement it in both off-chain side and on-chain side with smart contract, because the state is so clean. And there is another big issue from the memory architecture. In RISC instruction set, it's road store architecture model. So we don't have to handle the memory modification in instructions. It could reduce a lot of bugs, because think about it. If we I give an example. For example, the instruction. If we could do it directly on memory, yes, we could do that correctly. But how about another instruction? We have to do it again and again. But in RISC world, we only need to do one time. Just need to implement abstraction layer to do memory operation. That makes things much easier. So the state is clean. We like it, and here's another example. In the first figure, it's a function. So we can see it's a function about. It's very simple. It just want to give the count of the one in bit vectors in a bit vector, and it's the row code in Go. And if we compare it to x86, we could see the instruction listed here, and in RISC-V we could see much longer instructions, and we could just use one special instruction popcont to do the job. the purpose I show the results here is that if we use instruction sets like RISC-V, although we may it looks like make program longer, but it's okay for our purpose, because in the optimistic rollup in the interactive proof, we only need one step to be sent on the layer one, and the arbitration contract will only handle one instruction, and if the the future of the instruction is short. It's shorter. We could have a clear solution. Here is a very simple figures to show how it works. Before the step 0, we do the pro execution to get its own results, and load the emulator Wi-Fi input in the after the step 0, because someone may cheat here, and when we find the disagree step, we end here, and we just go backwards one step and replace it on the smart contract in layer 1. It's enough to get the right result. So the simple instruction side do help us. Okay. These reasons I just show, it may sound like it's not just for RISC-V. Maybe the whole family of RISC can be used in this purpose too. But why we choose the RISC-V? Actually, in the first version of our emulator, we use MIPS for testing, for understand the whole process better. And in the next version, we will use RISC-V because the community. We could see the community grows so fast in RISC-V world, and we have seen the power of community in blockchain world, and as the blockchain project we think RISC-V is the future. It could attract more developers to build on it, and that's the best reason I think. Okay. It's a very short presentation. Thank you.
Okay, go for it.
Okay, we're live? Okay. All right, great. So now we have the discussion panel. So I'm going to introduce our guest speakers today. The first one is Dev Oja, which please correct me if I pronounce that wrong. Could you just say he's the co-founder of Sika and a contributor to the Cosmos and Osmosis ecosystems. And could you give us just a quick background on yourself, the projects you're working on, and how RISC-V is being used in those projects?
Yeah. Okay. So I guess been a contributor to Cosmos since before the launch of the first Cosmos blockchain. Worked all over the stack in it, and helped make Osmosis one of the main chains in Cosmos. Also, I was a Stark researcher for several years. So then, how are we planning to use RISC-V in Cosmos? Like with this vision of getting a lot of the Cosmos code rewritten to make RISC-V the execution target of like what's considered official, then getting people to use like RISC-V binaries and simulate them in a VM if it's done on RISC-V hardware. And one of the biggest goals of this is to use like a Stark proving system, so we can have our validators like produce these blocks with a snark proof saying that this is valid, and everyone else in the blockchain can just check a proof that this happened rather than rerun the entire computation. And it seems like using RISC-V is the best way to get to this goal of like making it much easier to verify everything on chain.
Okay, and let's see. Next up, we have Eric Kaneda, software engineer at RISC-V. So same to you. Could you just give yourself a quick self-introduction, tell us about the project you work on and how RISC-V is involved with that?
Hi, my name is Eric, and I'm a software engineer at RISC-V. We're a proving service company and not an L2. I work on the ZK-VM as well as around it. And so the ZK-VM is like a virtual machine that will interpret RISC-V code to generate these proofs of computation. So we are, so basically like our product is basically using RISC-V to very, very closely. Yeah.
Okay, all right, great, thank you. And third, we have Shueji Xiao. I apologize in advance if I mispronounced that. I've been trying to get that right for 3 years now, and I still mess that up. He's a staff software engineer at Cryptape. Welcome, and same question to you. Could you please give a short self-introduction and then tell us about what you're working on and how RISC-V is involved with that?
Yeah, first of all, Jordan, I think you're doing a great job pronouncing my name. You're really awesome here. And
thank you.
So I've been working at Cryptape for like, I think 5 years or so. I'm the original author of PolkaVM together. Yeah, that's what we do here.
Great, thank you. Okay, so let's go ahead and move into the discussion topics now. So I'm going to read off the question, and then I'll go through a round robin style on the three of you to give your answers to it. So the first one is, why do you believe that RISC-V is a good fit for the blockchain industry, and what excites about the possibilities? So we'll go to Dev first. Could you tell us what you think?
Yeah, for me, I think there's like 3 main reasons. One is that RISC-V, I think, is a great target for or a macro reasons. I think in like blockchain, one of our goals should be to get all of computation very verifiable. Like this should be a thing we export to the rest of software. That you can, if someone else in the world runs some code, you can just check that all the properties of it are valid. Or if your laptop's running some code, you should know stuff like it didn't leak anything it shouldn't have to the rest of the world, or it did its job correctly. So I think RISC-V and like ZK-VM work with RISC-V, like stuff like Eric Shueji do is like pretty critical for this. And I think RISC-V is like the easiest way to get this for most software. It's a great compilation target, so you can use any existing language and just LLVM will compile to something provable. Then a second part of like why RISC-V is special, like you have another thing that could work for this, WASM, and up to some differences in like how provable it is. There's some like fairly nuanced details why I think RISC-V seems better, but if we want to dive into that, we can. But another one is that since RISC-V is like this quite nice open standard with like industry buy-in for hardware, or it's also can serve a second goal of like eventually we should be having very open like hardware standards for like actual CPU chips that can go in laptops. Because it depends on how tinfoil hat you're being, but there's some level of like security concern where if you want to know that there's like no way that data is being leaked out of a CPU chip and you're being very paranoid, like it's hard to get to it feels like a minimum requirement is that you can at least see what the hardware should be doing. And it seems like you have a viable path to get there with enough funding and at least a minimum open hardware standards.
Yeah, absolutely. I mean, I would add to that. I think we probably all need to have bigger tinfoil hats in this regard because we're looking at something, well, we're not looking at it. We can't look into a computer processor very well. So very important point. So same question to you, Eric. Why do you believe that RISC-V is a good fit for the blockchain industry and what excites you about the possibilities?
So my background is in operating systems, and I used to work at Intel. And so, I have witnessed a lot of things that, are pretty a little bit scary in that we, like the operating systems can call into code that they don't know if they'll return at all, right? So like a lot of this stuff is, it is good to have some sense of caution about what our systems are doing. And what I really like about using RISC-V for blockchains is that it helps blockchain engineers get outside of using software that's super specific to blockchains and to use software that other people, like other engineers, non-block developers, you're in this camp, so you work on this kind of software, and you're in this camp, so you work on this software. It's like a uniting thing.
Right. Yeah. I mean, I would say that's a little bit akin to reinventing the wheel. When you say it's like we need to be focusing on the same wheel, so we can make more progress on that. Yeah. So very powerful point. Yeah. So same question to you, Shujay. Why do you believe that RISC-V is a good fit for the blockchain industry, and what excites you about the possibilities?
Yep. So to us, the question is mostly about abstraction. So as a blockchain VM, we need the blockchain VM to be deterministic, meaning that every execution in everywhere should end up in the same result. Second property we want is security. It most likely in the terms of sandbox, it must provide enough security for us to secure all kinds of tokens and other activities on chain. The third property is performance. Apart from for a VM to be deterministic and fast, we also want it to be apart from the VM being determinist and secure, we also want it to be as fast as possible in terms that we can run as complicated applications as we can. And after satisfying these three properties, mostly about reducing overhead, we want the VM layer to be as thin as thin as possible to a normal CPU running on a laptop or on a desktop. So in terms of those choices, we think RISC-V is the I say that is most close to our everyday running CPU in our machine. So that's why we pick RISC-V. And apart from that, I also agree with the previous speakers saying that RISC-V is an open standard. So I think in 5 or 10 years, we may see open hardware running RISC-V, I say everywhere, and we also see pretty much every language out there is also compiling down to RISC-V, I say. So we're in a world where we're moving to one single open standard so everyone's using. I don't see blockchains should be an exception. We should really just embrace this open standard. So it's always my goal that we should be able to use pretty much any language out there, be it like Rust or C or C++ program compiled directly by LVM, or even using other language like Java compiled down from JVM or the C# or all these languages should pretty much be the same, and they should all be able to compile to RISC-V VM. And you should be able to pretty much use all this language to write smart contract program that running on RISC-V VM in the blockchain world. So that's pretty much my dream, and I think we're moving towards this area. So So that's my view and my idea of why RISC-V should be a best choice, because it's close to the hardware, and also it's an open standard we should all be using.
Yes, definitely. Thank you for saying that. And yes, I agree completely. I'm excited too about the possibility of hardware, open source hardware too, because we are all trusting these computers to execute properly and exactly as intended. And as we move into a blockchain future where so much trust is being put into these systems, it's quite important to be able to see deep in there. So let's move on to the next question. And this time we'll start with Eric on this one. Why was the decision made to use RISC-V instead of one of the alternatives?
So here at RISC-0, I was not with RISC-0 when this decision was made, but with the way that the Stark proving system is laid out, the main benefit over the other instruction sets, for example, so RISC stands for Reduced Instruction Set Computer, as opposed to CISC, a complex instruction set computer. And so CISC's instructions can do a lot of things at once. And the simplicity of the RISC-V architecture and the instruction set makes it so that proving is much faster compared to other instructions like WebAssembly, for example. We previously saw a slide that said 147 minimal instructions needing to be implemented. That will blow up the prover size, and that could really slow down proving, as well as increase memory consumption during proving.
All right. Yeah. So, I mean, definitely times have changed. I mean, I know that there's arguments for CISC definitely back in when computers were much less mature. So it's exciting to see the changes that are occurring right now, and that there's been such a big move towards RISC. And it seems like that's the way going forward. So next, Shujay, could you please address the same question? Why was the decision made to use RISC-V instead of one of the alternatives?
Yeah, so back when we started, it basically comes down to several choices in terms of blockchain VM. Some people will use EVM as the VM in Ethereum. Some people will use WebAssembly, and there are other people rolling out their own blockchain, the blockchain VM. So our decision process is we don't really want EVM because it's a different abstraction layer that's so high, that is higher than the abstraction layer we want in terms of a blockchain VM. In EVM, every integer you have the 256-bit integer. There's no 60-bit or 32-bit integer. Even your the range of a number will never exceed that range. So EVM is not the proper choice here, and we did consider WebAssembly, but we end up in the same conclusion as Jen from Polkadot saying the WebAssembly is one big standard that's it's always growing, and it's never going to be an end. Like we do a feature freeze on WebAssembly, and everyone use this instead. So WebAssembly is starting out as a standard people use in everyday browsers. All modern browsers like Chrome, Edge, or Firefox, they are updating every few weeks. So you have a concept called evergreen browser, meaning this browser is always updating, and you have to keep them up to date to the official version so as to be free from security leak and other things. So they get this chance they can be upgrading this forever. It means that all standards living in the browsers will continue to be receiving new updates using new opcodes or different things. So WebAssembly, if you look at it from a browser perspective, it makes perfect sense to have a WebAssembly in the browser. But WebAssembly, if you look at it from the blockchain perspective, might not make so much sense, because we all know that upgrading blockchain is a risky operation and we only see upgrades to a blockchain every few years, or even slower, even more rare than that. So you definitely want the IC running in your blockchain to be as stable as possible. So a hardware IC like RISC-V makes perfect sense here, because it's not like we're upgrading our laptop like every day. We're upgrading them like only a few years. Some people even use their laptop like for 10 or 20 years, like all the ThinkPad fans. And so we do believe that, so in this perspective, the hardware VM makes more sense to us, so that will land us on RISC-V in the first place. The other thing we value in RISC-V is that instead of rolling our own VM, RISC-V is an open standard. People will bet on it. You see people contributing code into LVM repository, enhancing RISC-V support every day. So we're not building our own solution where we need to build our own tool chain, everything from the ground up. We're embracing an open standard where we can contribute to LVM and we're enhancing CKB-VM in the same time helping everyone in the RISC-V ecosystem. And on the same time, we get to receive people's improvements in the RISC-V system every day. So together we are building an open standard. So these two reasons are the reason that we believe RISC-V is better for than the alternatives like WebAssembly. One being number one reason that RISC-V is simple and deterministic, and the standard is free and it's not going to receive updates anytime soon. The other thing is like RISC-V is an open standard. We're jointly in the community building a thing that's going to be there for the next 20 or 30 years. So that's our reason picking RISC-V than the alternative.
Yeah, very well said. I mean, I remember long ago, I was actually a supporter of using WASM in blockchains, but in retrospect, it's kind of a big mistake. I mean, for all the points you noted, it's built for browsers. It does a great job in browsers, but browsers are quite different from blockchains. So Dev, you're up next. Could you please answer the same question? Why was the decision made to use RISC-V instead of one of the alternatives?
Yeah. Okay, I want to make one point that I don't think has been hit on, at least, which is that RISC-V is also just really simple. Like I was lucky enough to go to UC Berkeley when they had after they did the switch from MIPS to RISC-V. In the intro class where you first learn C, what is this thing called memory in a computer? What is a register? You also have like this 4-week unit at the end of the class, which ends in your final project being writing like a hardware, the entire data path of like an ALU for the entire RISC-V ISA, except syscalls, whatever. Besides syscalls, you've written the entire thing. Like it is sufficiently simple. This is a thing you take people who've never touched C before to doing at the end as a final unit of a one semester class. Same thing, similar stories for like writing interpreters for RISC-V or compiling Python to it in like other classes. Like RISC-V is an exceptionally simple ISA, which is to its benefit. So then this just makes you feel good at RISC-V. It's not a reason to use it, but then, it was one of the reasons to use it. But then, maybe to elaborate more on the story for like doing proofs on RISC-V, where the macro goal of a proof is that someone else can run some RISC-V code, can do a proof. You can check the proof that the code is executed correctly without having to trust the server at all. Well, since RISC-V is a really simple ISA, it actually something that's interesting comes out when you look at the history of snarks, where the internal to do a snark proof, you have to have some mathematical representation of the program you're trying to prove and verify. But we had this arc of snarks designs went through something very similar to CISCs, where we started with this really simple but way too limiting form of instructions. Then we started expanding them to this thing called R1CS, which is basically like kind of like infinite fan-in addition gates and like and multiplication gates. Then we realized this is still like not enough, so we built this thing called AIR, which is super complicated, like probably more it's in many ways more complicated than like x86 even. And we realized, okay, well, this is giving us a bunch of scaling issues. We need to constrain this. And so then, because it was too hard to build programs for and too hard to like make fast proofs, so we kept on constraining it until we started getting things that looked like programming with a handful of gates or a handful of instructions. So now this RISC-V, comes along and it looks like, okay, here's this instruction set that's really good for hardware and has very few instructions. It seems like a very nice fit with this how these proof systems are working underneath of went from this very complicated thing to progressively simpler and simpler. And so the only real alternative, the question is WASM, and I think Shreja hit on many of the points of why it just seems like RISC-V is a generally better fit than WASM. The details for proving systems are pretty in the weeds. I'm hesitating because I don't know if this is an interesting thing for the audience of going in the weeds of potential things in Snark then that makes it look like RISC-V is better, but.
Right. Well, yeah, I mean, I see exactly what you're saying. You're saying we're dealing with systems that are complicated enough. We need to maintain the simplicity at the base layer if we can. So yeah, absolutely a good point. And so let's move on to the next question though, before we run out of time. So Shuji, this one will be to you first. How will end users benefit from RISC-V?
First of all, we're seeing new hardware every day. I'm personally thinking that my next laptop will be a RISC-V based computer. So I think that sooner than later we'll see RISC-V in our phones and in our laptops. And that's definitely a huge step forward for us to embrace open hardwares where we're seeing more devices that we know that don't consider any malicious code, and we can simply replicate them ourselves. On the other hand, I think that RISC-V being an open standard is also attracting more and more developers. We see all different languages porting to RISC-V right now. We see LVM and Rust has already supporting Rust code, and Nervos we are writing Rust code and Rust-based smart contract every day. We're compiling Rust code using the official Rust toolchain to RISC-V so as we can run in CKBVM. And we're also seeing other programming language porting to RISC-V as well. On Java and .NET, those enterprise levels language are both being ported to RISC-V. As we are seeing more hardware using RISC-V, and we're seeing more software being written in RISC-V, and also more programming languages supporting a RISC-V platform. I think, and in general, we're moving to one big standard that everyone's using. Everyone's pretty much speaking the RISC-V language here, and I believe that'll bring us a better verifiable platform and also more secure and performant platform because we are all contributing on the same thing, and I believe that will make innovations going even faster. And in a really distant area, you see that Facebook is also using RISC-V as a chip to build their next AI artificial intelligence platforms there. So really, the whole industry is betting on RISC-V. And not just, I see beyond the blockchain space that I think that all the blockchains are going to benefit from RISC-V, and also all our everyday computing platform, all the technology we use here is really going to benefit from the joint effort in RISC-V community. So together, I think we're witnessing Linux in the 1990 areas that everyone's contributing to the same platform. We're building the same next big thing. So that's my personal vision here.
All right, thank you for that. So yes, momentum is very important in our industry, absolutely, and we're starting to see a huge amount in RISC-V. So same question to you, Dev Oja. How do you believe the end user will benefit from RISC-V?
I think the biggest thing is for hitting on this verifiability dream of getting more code on blockchains to be verifiable with proofs. This is huge for users. And a second is, or if you get more code on the web or in an Apple Watch to be verified, right? Then just you're reducing so many tail risks that users take on today that they just aren't aware of. And so then the reason for RISC-V there is that this is this amazing target where you take your existing code, don't go rewrite your smart contracts. I don't know, if you're some statistics website, don't go rewrite your all your statistics code from Julia or R. Just toss that into LLVM, compile to RISC-V, it should be minimal overhead, and we can have the proofs be made for you. So the idea is like I think the big benefit to users is getting many tail risks eliminated, or just getting data on the web to be like authenticated. Like, I don't know, imagine you have an extension that gives a green check mark if any number you see has like a proof that the stats were computed correctly. Then this is I think this is exciting for just reducing the tail risks we have in software as a whole, which is actually a little bit that's one goal. The second, I think, is a much more as a grander ambition of like open hardware over a 10-year timeline. But this first one doesn't depend on even hardware shipping. It's really that this is an amazing compilation target and proof system and great proof systems.
Yes, absolutely. I share that as well. I love being able to use the same languages and compile for a smart contract, compile for IoT devices. I have a chip that's about this big. It's about the size of a quarter. It's an IoT device. I can use the same languages and everything. It's very important to have that reuse and to continue with that, with the momentum that Shujay was talking about. So same question to you, Eric. How do you believe end users will benefit from RISC-V?
I'll take this in kind of like a ZK sort of ZK applications kind of approach, but yeah, right now, I'm able to, it's actually very fun that our software uses RISC-V, because what I do on various occasions, we had like a hackathon about 2 weeks ago internally at RISC-0, and I decided, there's this really interesting database crate. I wonder if I can enable it on our system, and I was able to do that. So, and it only took an hour or two, and it wasn't like completely seamless, but I was able to basically get a database library to work, which meant that I could create a table, insert some values, and fetch some values very quickly. So I think as far as the end users, I really hope that they will get to use more software more quickly, and better quality software as well, because this for example, with my database thing, this is someone else's work that they've database. I'm not a database expert, but like database experts have collaborated on this to create such a great crate that I could reuse. So
Yes, reuse, especially between different domains. I hadn't even thought about that one. That's a very important one as well. Okay, so let's continue on to the next question. So this one will go to you, Dev. What are some of the challenges in adopting RISC-V?
I think one of the biggest ones is there isn't until Jay's talk earlier for PolkaVM, there hasn't been as much production grade deterministic VM demand for RISC-V from industry outside of blockchain. Where with WASM, there's this very nice thing where basically a lot of the cloud computing, like AWS Lambda and stuff, cared not just about having a WASM VM. Every browser cared about WASM VM, but Lambda and folks cared about it being extremely deterministic. So they invested a lot into WASM-I and WASMer. Whereas for RISC-V, we didn't really have this. It's kind of on the blockchain industry to kind of build something that's very fast and has high determinism guarantees on our own. And it's been really encouraging to see the PolkaVM talk was shocking to me earlier that it's actually beating the WASM the best deterministic thing for WASM, which is insane. And I think that was in my head one of the biggest challenges. There's some smaller ones, which I think is just improving a lot of the some of the tooling for getting code that takes advantage of both 16-bit, 32, and 64-bit RISC-V modes in one. I think it's actually a really cool optimization for making RISC-V code better for proofs than WASM. But I think that's a much smaller thing. The biggest in my head was the VM stuff, which actually seems solved.
Okay, all right, thank you for that. Eric, same question to you. What are some of the challenges in adopting RISC-V?
Let's see. So one of the challenges that I've actually been running into lately is that we actually found some bugs in LLVM for RV32IN. So software is not perfect. So like and when we're using all these tools, we have to kind of understand that it's changing all the time, and there's going to be some bugs. Luckily, one of my teammates filed a bug. They resolved it very quickly, and now it's backported. But and I think that's also what it means to use free software as well. Open source software is that we're also contributing to its improvement. Another thing that kind of crops up in challenges to adopting RISC-V are the source languages. So Dev and I had like a short conversation on Telegram about using Go. And so a lot of people will say, oh, can we run Go code on these ZK proof systems? And I always hesitate just a little bit because Go's runtime is really complicated. And so that actually adds cost to the proving system. So in particular, Go is really great for concurrency and memory management. But in ZK, we actually pay for that. Every single instruction that's involved in garbage collection and scheduling, we actually pay the price, or like the proofs constitute those costs as well. And sometimes it's also about mapping what it means for a concurrent language and how those constructs will map to our execution environment, which is single-threaded. So there are some challenges, but I think they're really, really fascinating. And by using RISC-V, we're able to just kind of jump to the next phase and say, okay, we have an ISA, we have languages that compile to this. Now, how can we, do the work to fit it together? So.
Right. Yeah, definitely. Tool chain challenges can be a pain sometimes, but we will move past them as an industry. Same question to you, Shujay. What are some of the challenges in adopting RISC-V?
Yeah, on my mind, I can think of two. The first one, the same as the other two discussion speakers here. So it's mostly about the tool chains. Back in 2019 or so, when we were getting started, the RISC-V supporting LVM and also to an extent in GCC is really premature, and we run into bugs and rough cases everywhere. So we have to be very careful, figure out a path going forward, and be strictly sticking on obeying this path so we can get a working program. Things have gotten much better right now, but still there are rough edges, and we have to do some work to accommodate for this different this really new area of RISC-V support and different compilers and all the different code generators. And the other thing that we frequently run into is performance. So we're not running into performance because our VM is slow or something. We are continuing making the VM as fast as we can. But the thing we run into is that the code generation quality in modern compilers such as Rust and our VM is now the code generation quality in those backends for RISC-V is not as good as code generation quality for x86. So yeah, x86 backend has been here for like 20 years. People have done enough optimizations on them, but the new backend for RISC-V has just getting started. We see a few years development, people's part-time development effort on that, and part on that, and you see none more optimization efforts. So frequently you see the same code compiled. You use the same piece of Rust code or C code compiled to x86. You will see totally different code generation pattern from the code generated for RISC-V platform. So there are times we need to hand code certain RISC-V assembly to make sure the code is running faster. Things are getting better, but every now and then you still run into these edge corners where you need special hand optimized code so as to make the RISC-V code run as fast as possible. So I would see those are definitely the challenges. Things are getting better, but we still see those challenges. And in a different perspective, this is where all the fun we have right now. So yeah, we see challenges and we try to overcome them.
Right. Thank you. Yeah, I remember some of those compile problems as well, trying to write some early smart contracts on CKB. We'd get bizarre little errors here and there, but thankfully they've now resolved themselves. So the entire tool chain, including the compilers, are definitely getting better. So next question, final question before our bonus question. This one goes to you, Eric. What are you looking forward to with RISC-V in the future?
In general, I really appreciate how it, so when you look at the RISC-V specification, you have these different features. And I'm looking forward to having the RISC-V community retain those features and say, okay, well, this part of the specification is frozen, like this is complete and this is complete. So I'm really looking forward to the continuation and the stability that it provides for other developers like me.
Yeah, we definitely need that kind of stability. I mean, like you were saying earlier, the tool chain still work in progress. Stability is good, especially as we move forward and have systems that are more dependent on these systems. So let's see. Same question to you, Shuche. What are you looking forward to with RISC-V in the future?
I'm definitely looking forward to see more extensions helping us achieve better programs in the RISC-V space. One thing that I personally have an eye on is a new RISC-V extension called RISC-V CFI. It's designed particularly to overcome a particular type of attack called return-oriented programming. So this is a particular kind of attack that an attacker is now injecting any malicious code, as he is reusing code in our existing program so as to achieve their goals. The attack, I would say, pretty much really clever, but clever in a bad way. So if you're interested, feel free to Google it afterwards. So, and the RISC-V community took a look at the state-of-the-art RLP attacks and also all the mitigations we can do to prevent them. And they basically designed a new RISC-V extension called RISC-V CFI. So for all the processors that incorporate this design decision, this new extension, it will help you avoid this return-oriented attack as much as possible. It's basically the state-of-the-art result we can have in modern processor design. So personally, I think of incorporating this new extensions into CKB-VM to help us write more secure programs in the future. It's all this new advancements, all these different new extensions that really excites me, and I'm eager to see more in the RISC-V space in the future.
Yeah, thank you for that. Yes, absolutely. Security is an issue, and anything computer related, we have horrible problems with security still to this day. So any improvements to that, especially at the hardware level, very important. And I hadn't heard of that one. I'm actually going to be looking it up after we get off of this presentation. So same question to you, Dev. What are you looking forward with for RISC-V in the future?
At the ISA level, this might be a bit silly, but just the vector extensions in RISC-V are so clean. Like, if you've ever had the painful experience of having to look at SIMD stuff, of like the names are nonsense for every SIMD instruction, where it's like you want to do one operation, so like I don't know, add two numbers, but then I want to add two numbers for I want to add two lists of length 1,000 together. Or there's these SIMD instructions that just kind of do that operation faster. In every existing thing today, SIMD is like a mess. You have so many instructions. You have different your processor hardware has to implement a different instruction for 256-bit register size, 16-bit input, 32-bit input, 64-bit input. The vector length stuff in RISC-V is just took a ground-up reimagining of, okay, well, what are we trying to do? How can we make this maximally simple? It's like, okay, well, they show a way of like, let's like flexibly let people choose between 16, 32, 64, took the learnings from hardware data paths over decades and found a thing that looks like as speed competitive, if not better, due to less instructions, things that achieves everything you want with far lower developer complexity and hardware designer complexity. So like, in the RISC-V spec, I think this is something that's insufficiently appreciated. But as we're reimagining just what you can do with your ISA or this common convention for executing like programs in it, it also seems like you can reduce even more just standard memory bugs that plague us in all non-memory managed programming languages.
Right. So let me translate that a little bit for the average user at home. He's saying that things that are good for the developer means better products for you. So it's a very important thing. We definitely love these little features that are coming out. So I think we still have a couple minutes here. So we'll go ahead and we'll do the bonus question. And this one will go to you, Shuji, first. Should RISC-V be used inside ZK? And that's zero knowledge we're talking about.
Yeah, so I'm gonna throw on a slightly controversial, slightly different opinion here. So I personally have my doubts using RISC-V as an ISA inside a ZK proving system because, as Eric just mentioned earlier, people frequently ask you if they can use different programming language on your blockchain, and people would say, "Can I use Go on in your system? Can I use JavaScript in your system? Can I use Python in your system?" You see, if we only let people write C or Rust program and compile that down to RISC-V and then compile this RISC-V program into ZK circuits and prove that, things might be okay. But to support higher language like Go, JavaScript, or Python or different things, you definitely need to include all this runtime, including a full-fledged garbage collector into your proving system. That will complicate the proving system. And a lot of the actual circuits is actually done to support the garbage collection, which might or might not be wrong in the final program. So I'm sure that all the different groups are improving ZK proving system and making this problem less of a problem, but still it really depends on your problem domain. If you're building a sophisticated program, or if you're using a very simple program, for certain use cases this might not be working so well. So personally, as a personal opinion, if I were to introduce ZK to Nervos ZKB, I will use a different solution. In that, I will use a slightly higher level language, like likely a JVM or a JavaScript or different language, and I will compile this language into a higher level ISA and use that ISA as the ZK proving system. Then we can compile the ZK fundamental verifier code down to RISC-V so we can run in the ZKVM. So this might just due to we are having a different architecture, but I must say I have my concern as of right now regarding using RISC-V as the ISA in the ZK proving system. I think RISC-V definitely makes sense. You will compile down a RISC-V verifier to RISC-V code, but using the RISC-V ISA directly in the proving system, I think it really depends on the problem domain. If this so we can say if this is a good fit or not. For our architecture, where we're compiling all these different crypto primitives into a RISC-V program, we might have a harder time incorporating this design. So that's my personal opinion.
Very interesting on that. I must admit it's a little bit above my head at this point. Dev or Eric, would either of you like to respond to that?
One thing is I'm actually it's not obvious to me why garbage collection is even an issue. So the nice thing about a snark or these zero-knowledge proofs is you first execute the program, and then I'm doing a proof that I want to verify something. So one, there's a couple of tricks that actually happen in this that are a bit non-obvious. Like for instance, let's imagine division takes 10 times longer than multiplication. Well, what I can do is if A divided by B I claim equals C, you can check that answer by saying, does C times B equal A? So you have this advantage of you can check things faster than you can compute. For division, this might not be an obvious example, but square roots is a better example, where square roots takes God knows how many instructions natively. In checking a square root is easy. What's, I don't know, square root of 2, I tell you it's 1.41. Good luck figuring that out. well, good luck figuring out how to compute that. But you can just multiply 1.41 by itself and see it's near 2. You believe me. So something like there's a fundamental trade-off you have with snarks. So for garbage collection, and what's going on? Well, you have a bunch of memory, and then you're saying some of it's useless. I have to go find it. So finding it's expensive, but showing that there's no references is a cheaper thing. You just have to go edit the garbage collector of the language, which most languages like offer as a thing. This is this is actually part of the process of getting like normal code to be embedded code of like you do things around the allocator and garbage collector. But one step further, I'd actually even challenge, is that needed? Because even the way you handle memory doesn't actually need to be kind of in RAM of the prover. You could kind of like store it somewhere else into like a separate Merkle tree, and just like, who cares if there's extra stuff in there? You don't have to like, once it's garbage collected, you already know it's garbage collected. You, the prover, can just forget that leaf forever and just keep it pending to the tree. Yeah, I guess maybe my response to the garbage collection point, and maybe I was missing the forest for the trees, but it just helped down.
Fair enough. Fair enough. Eric, do you have anything to add to that?
I was thinking the same thing as Dev for dealing with garbage collection, but I do think that it does, like, you need to use, at the end of the day, like, people do need to use the right tools to solve their problems, right? And I guess one kind of counter to this, using, well, one of the reasons I guess like to compile down to like maybe like a higher level language is to maybe have like better control over domain specific things. But if you think about it, like a lot of these cryptographic libraries, they're also, that run on our machines today, they're also like C programs. They compile down to x86, ARM, whatever your computer runs. And so I don't really see that much of an issue. We also get to take advantages of all these developer tools that have been created over the past, I don't know, 50 years or so, to ensure that you write correct software. And I think that's one of the main advantages of RISC, using these tools. It's like, hey, you're using all these time-tested tools to develop correct software, rather than inventing a new language that has new semantics. Now you need to write all the tools and teach other people how to use it properly, right? So that's my case for using RISC-V inside, or like well-defined ISAs inside ZK, as well as which RISC-V is one of them. So.
All right, so thank you for that. So unless there's anything left from the three of you on that topic, I should offer that, Shujay, any response to that, or should we just agree to disagree on this for the day?
I'm personally ready to be proved wrong, but let's see how things go from there.
All right, fair enough.
I would want to add one thing for clarity to people in the audience, where when we say like RISC-V as an ISA in like the ZK systems, we don't actually ever mean the ZK system is only dealing with RISC-V as input. We imagine in our heads we've actually amended it with a couple more operations, like a couple more opcodes or a couple extra instructions as well, for things that are needed in just for the internals of snark management. So it's because you can imagine that your proof has to verify some things with other proofs, and this is pushing that to being RISC-V as well is like just increases cost by a couple large factors. So we do amend it. And what does this look like? It looks like we add a SHA-2 hash that's native, or fancier hashes that probably never heard of. So it's not literal. It's not going to literally be RISC-V, but it'll be RISC-V like plus a couple minor extensions. I just want to, I don't know, maybe it's just a note of getting the right impression out.
Well, the RISC-V instruction is meant to be extended through the system calls anyway, so
True.
I think as long as you kind of do it that way, like it doesn't really matter. And you define it, of course. So
Is that for proof recursion or just other things as well?
Proof recursion is the biggest, but then also for your but like proof recursion is this fundamental like thing if you're trying to chase low latency stuff. Like this is a fundamental building block. But then I would expect that also just for the apps that want to use it in like blockchain context, this is a product market fit requirement to have a faster hash than.
Got it. And yeah, Eric, I'm sorry if I sounded like I thought RISC-0 was an L2. But you guys are just only, as far as I'm aware, you're only used by L2s, right? Like there's no L1 that is pursuing using your system. Is that right?
Not familiar with those. I think there's a lot of L2s, I think.
Yeah.
I'm not on that side.
I mean, I can add to this. In Cosmos, we have this other VM environment called WASM, and there are some WASM contracts that are actually using RISC-V code or RISC-V verifiers and provers in them. These are for like small apps in like as contracts, like so it's not like the full blockchain, but it is blockchain like code or apps who's taking advantage of RISC-0.
Very cool. I guess, do you want to call out like what is that they're running? What chains are they running on? I guess would be the right question.
Juno is like the Cosmos chain that I'm thinking of they run on. I wish I could remember the app names top of my head.
Sure. No, I think that, just knowing where to look to begin with, I think gets you pretty far. So I appreciate it. Yeah, I think we're done. Yeah, it's we're at the top of the hour, so we're on time. Wow.
Yeah, that's perfect timing. All right. All right. Well, anything you'd like to say before we wrap up then, Matt?
No. Yeah, goodbye to the YouTube. Thanks for joining. Yeah, it looks like we had a number of people come on. Yeah, thank you to Eric, to Dev, to Jan, to Shujay, to Popcorn, to Jordan. Thank you for joining. It's been a great conversation. Yeah, I look forward to more of this. This is it's exciting to see RISC-V really coming into its own. So
yeah, definitely exciting stuff. Well, anyway, thanks everybody for watching, and thanks to our panelists and everybody who spoke earlier, of course. And thanks to the YouTube algorithm for supporting us today. For once, we actually got a massive boost in the middle of that thing. So anyway, yeah, that's all I got. Take care, everybody.